Alrighty then. 2.3, section 2.3, interpretations of the derivative. So far we've talked about what the derivative is, and now we just want to think about what it means in a business context. All right, so in this section we want to introduce some notation and just getting used to using words to explain the numbers that we get, basically. All right, and have a couple formulas for you. All right, so let's get started. So remember before we talked about how to estimate the derivative from a table. Basically, you just use the average rate of change formula, since the slope is the derivative in a sense. So we could estimate the derivative when t equals 1 just by using the average rate of change between t equals 1 and t equals 2. And when you do that in this example, you get 4 feet per second. Okay, you could also use the average rate of change between 0 and 1. That's reasonable. You could also just, since you want to know the slope at this point, you could also use the neighboring points. You could use 0 and t equals 6, or sorry, t equals 2. These 2 points, that'd be reasonable. It would be unreasonable to estimate the derivative at t equals 1 by using the average rate of change between 1 and 4 or something like that. Okay, we want to get points that are close to each other, as close as we can. In a table, we don't have very many options. We can't choose like 1.1, 1.01, that sort of thing. All right, so this is the best we can do in this case. All right, and remember that since we are, in the end, we're finding basically the slope, then the units, whatever you get, the units will be whatever the units would be for a slope. All right, so if we're talking about the height function as a function of time, then the units for the derivative will be the same units for the units that you'd use for the average rate of change, which is feet per second in this case. So keep that in mind. All right. Now we're going to learn a new word today called interpolation. We're going to learn to interpolate data. All right, it's a very fancy word for basically estimating what a function is doing for values that we don't have. So for example, we have on this table function values for x values that are basically whole numbers, 0, 1, 2, 3, and 4. But what about 1.5, 1.25, whatever? We don't have those. But we have a way to estimate what that would be. We have a good way to do that. So let's do that. So we found before that h prime of 1, we estimated that to be 4 feet per second. So let's remind ourselves what this is saying. This is saying that each second, the height function is increasing by 4 feet. Get off that. All right, each second the height is increasing by 4 feet at this point. All right, on average. So that's if you go 1 second. But if you go, say, a half second, then you'd expect half that change, right? And if you go a quarter of a second, you'd expect a quarter of this amount of change, and so forth. All right, so a half second, we would take half the amount of change, which is 2 feet. So the way you get this change in general is you just take whatever the derivative is and you multiply it by however much that x value is changing it by. All right, here's a little formula. And notice it comes directly from the slope formula. Remember I said that slope formula was important that we learned? All right, yeah. Everything comes from the slope formula. If this doesn't look like the slope formula, I've just multiplied both sides by delta x, or change in x. Okay. So slope equals the delta y over delta x. When you multiply by delta x, you get this. Okay. So here the derivative, that's the slope. Delta t, that's like our x value. Okay. So for example, from time from 1 second to 1.25 seconds, how much time is elapsing here? A quarter of a second. So we'd expect a quarter of a change. And right. And so this actually isn't used right on this slide, but I'm going to give you this formula. This is actually the formula that you're going to use on your homework. That if you want to estimate the function at a value in between values that you have, you'll use this formula. So, for example, maybe you want to go a quarter of a second further than 1, then you would just put in 1, and the difference between 1 and 1.25, that would be 0.25. And then you would just put in your numbers and see what you get. Okay, I think we have an example here for you. All right, so here's the formula. And we want to estimate the height at 1.25 seconds. So we'll start, so we want to know what happens in between here. We'll start here, we'll start at 11, and we will add the amount that it changed, which is the derivative times the time elapsed. So 0.25 seconds, and the derivative was 4 feet per second. And when we do that, we get 12 feet. Okay, I hope that made sense. This thing is kind of hard to explain. Really, you just have to do it, honestly. So my advice, if you don't understand it, is try to imitate exactly step by step what I did, and then later on you'll understand it. You don't necessarily understand it before you do it. That's the point I'm trying to make here. Fumbling around. Okay, so anyways, that's that. That's how to interpolate data. Values and functions. You can also extrapolate. I could estimate what the function is at 4.5 or something like that as well, but not going to do that here. All right, so done with that for now. Now we have some notation to show you. So remember the slope formula. Slope is change in y over change in x. And now we're going to, but now we have a notion of a slope at an exact point, not an average rate of change, right? So we have the derivative, f prime of x, and we have a way to write this side of the equation instead of a difference between two y values, we will write that as dy dx. Right, so this is another way to write the derivative. So f prime of x, this is the most common way that we will use it. F prime of x. Whenever you have a function, you take its derivative, you just put a little apostrophe symbol, little prime. Right, that means that's the slope function, the derivative. But another way that it's used everywhere is dy dx. So you just need to know that. You need to know it, dy dx. That's how it reads. All right. So at a particular x value, like if you wanted to plug in x equals a, then the derivative at a is we just enter in a for x. We just substitute. We literally just put in the number there. All right. But on the right-hand side, we don't put dy dA. We never do that. They write a bar and then whatever you're substituting in for x. Okay, this is just a conventional notation, just the way they write the derivative. It looks weird until you use it a bit and then you get used to it. All right, so these are two ways to write the derivative. All right, now writing the derivative, f prime of x, this is my preferred way to write the derivative. Use it whenever I can because, I mean, it's less characters to write, it's quicker, but also I like f prime of x because it emphasizes that the derivative is another function. All right, that's key. It's another function, and it looks like a function, f prime of x. You got parentheses x here. All right, just a prime symbol to let you know you've taken the derivative once. Okay, dy dx, well, how is that helpful? Well, it helps Leibniz, one of the co-founders of calculus, feel useful, even though he's been dead for hundreds of years. Still got to be sensitive to his feelings. All right, so that's that. just know that that's a thing, and that's how we write dy dx. Okay, let's move on to see an example of using Leibniz notation. So typically, we'll talk about things in this class like the cost function, the revenue function, the profit function, that sort of thing. So if we have the cost function, capital C, of Q, being the cost to produce Q items. So what are two ways we could write the derivative of C of Q? Well, we could put a prime symbol, or we could write dc dq. All right, we say dc dq. We don't, for some reason, we don't say dc divided by c dq. We just say dc dq, and it's understood that there's a fraction in between what I'm saying. All right, so you'll see that frequently come up. All right, now what would be the difference between, for example, c of 10 and c prime of 10? What do these both mean? What's the difference? So make sure you're clear on that. C of 10 is the cost at 10 items. So the cost to produce 10 items. That's what C of 10 represents. It's an expression for the cost to produce 10 items. All right, we don't necessarily need the actual number, the actual cost, to talk about what that means. Okay, then C prime of 10, on the other hand, that would be how much the cost changed, the rate of change of the cost function. So that'd be how much the cost changed if we produce one more item. Remember, that's how we interpret the slope. As we change x by 1, which in this case is q, by 1, we look at how much the y value or cost changes. All right. And we've mentioned before that this is the idea of marginal cost. Right? It's the cost to produce another item. Okay. And this is the last thing that we, what is this? What? Okay, I think I copied this slide. Okay, so I don't think I need the previous slide. This is the last thing that we need to talk about today. It's relative rate of change. Now this honestly doesn't come up all that often. It won't come up for us that often, and it doesn't come up in, I rarely see it, but you do have a couple homework questions on it, so I'll just tell you how that will go. So we have a term here for you, which is not super important, but it's called the relative rate of change. It comes into play for things like exponential functions, which, remember, they change by a constant percentage rate, right? Anyway, we have a formula here for you. It's the derivative over the original function. Okay, it's this ratio of the derivative over the original function. And it gives us a sense of how much it's changed as a percent, not just how much it's changed overall. Right? Like if it's changed from 1,000 to 1,010, well, that's a lot less significant than changing from 10 to 20, even though the actual change is the same. So this will kind of help put that in perspective. Like I said, though, it doesn't come up all that often for us. But here's how a problem like this will work. So let's say we have a function f of t, and it represents the number of Facebook users t months since the start of 2015. All right, and suppose that there were 1.55 billion users at the end of September 2015, and that grew to 1.59 billion users at the end of December of 2015. All right, and we're asked to find the relative rate of change at the end of December of 2015. So we know we're going to use this formula here, f prime over f. What's a going to be? Well, a is an x value. In this case, we're talking about the end of December 2015. So would that be, let's see, t is defined as months since the start of 2015. So if I'm at the end of 2015, I've elapsed 12 months, right? If I'm at the end. All right, so I've got that. A is going to be 12. So let's first find both of these. Let's find f of 12 and f prime of 12. So f of 12, am I given that? That's the amount of users at the end of December 2015, it actually gives that information to me. So I found that. So now we just got to figure out what's f prime of a. Well, we don't have a function. The best we can do is estimate the derivative, and we will do that as we've done that before, like we did at the beginning of the section as well. We will use the average rate of change formula. Right, so the derivative, we will estimate it by taking two values that are relatively close to each other. All right, so we'll use the average rate of change between the two data points that we have, which is the end of September 2015, which is 9 months after the beginning, and then we're given 1.59 billion users at the end of December, so that's 12 months after the beginning of 2015. All right, so I use the average rate of change formula, and I just plug in my numbers. And what I got was 0.0133 billion users per month. Why did I write billions of users per month? Well, the top was the number of users measured in billions, and the bottom was a difference of years. So that's going to be years. Months. A difference of months. And so that's per month. So that's how I came up with my units there. So then, if I just plug those in my formula there, I have this as a relative rate of change of, relative rate of change of f prime of 12 over f of 12, and I just plug those in, and I got 0.0084, and I can write that as a percent if I move the decimal two places, so that's 0.84% per month. All right, that's that. All right, so I hope that made sense, and good luck on your Widely Plus as always, and have a good day. All right, goodbye.